Hello everyone, in this third module of our short course series, we will be revisiting the famous mighty calculus. In the first part of this module, we will be studying limit of functions. In the second one, we will be revisiting derivatives and integral. And in the third one, we will look after some applications of limit, derivatives, and integrals particularly in electrical engineering field. And for the limit part, we will first see what the calculus exactly is, and then we will give a definition of limit, both an informal and a formal definition. Then we will see how we evaluate a limit, limit of a function. We mostly focus on graphical evaluation and graphical representation of functions here, but we will also touch some numerical evaluation, and we will give some tips and tricks about this kind of evaluation. But we will not include analytical evaluation of limit of functions, because calculus is a huge topic, and limit is also a very big topic inside calculus, so we do not have time nor space within this course series, so we will leave analytical evaluation of limit of functions outside of the course schedule. But if we get some demand from our students and professors in next chapters, we can expand the topic to cover analytical evaluation also. So let's see what is calculus. Calculus is basically the mathematics of change, the mathematics of changing things. So what we are talking about is dynamic systems, whereas the mathematics earlier than calculus is just for static systems. So if we are talking about a dynamic system, it could be a time varying system or frequency varying system, etc., or velocity varying system. So if some components within a system change their speed by time, then this will be a dynamic system. In quite other words, calculus is also a limit machine. Here below you see an illustration concerning pre-calculus mathematics applied to limit process, and we get the calculus of today. Here we have an example. An object traveling at a constant velocity can be modeled with pre-calculus mathematics because it is a static system. But to model the velocity of an accelerating object, which has an increasing or decreasing speed, then we will need calculus. And to proceed from pre-calculus mathematics to calculus, we use the limit process as an interchange. There are two very classic calculus problems. These illustrate how the concept of limit is used in the calculus. The first one is the tangent line problem. Finding the slope of a straight line is a more basic pre-calculus problem, but finding the slope of a curve at a given point, P, is a more complex calculus problem. So here in the figure on the right side, you see one straight line that has an angle with the x-axis which is not shown here in the figure. And we also have a curve, the blue curve. It represents a function. So finding the slope of that curve at a given point is a calculus problem. And the limit process is to compute the slope of a line through P, the point P, and another point Q on the curve. As the distance between these 2 points decrease, the slope gets more accurate. And the second problem is the area problem. Finding the area of a rectangle is a very straightforward pre-calculus problem. But finding the area under a curve is a much more complicated calculus problem, because for any rectangle we have basic formulas, but for a curve we only have the function of that curve, but no formula for the area of that curve, the area below the curve. And this is where the limit process involves. Sum up the areas of multiple rectangular regions would help us to estimate this area under the curve. So as the number of rectangles increases and their width decreases also, the approximation of this area would improve. The basic idea here is, in order to find the area under the curve, the area between the curve line and the x-axis, we can put multiple small rectangles and we can combine the area of these rectangles, and we will find something very close to the real area under the curve. And if we increase the numbers and make the rectangles smaller, our accuracy will be better. This is the main idea. Let's look at an informal definition of the limit. The limit is taken as the input, and the variable x approaches to a specific value from either side. And in the given example here, variable x is approaching to an arbitrary constant c. And we use this notation, limit fx equals to L, where x approaches c. So this is the basic generic notation of limit of a function. The limit itself is a value of that function. This means that it's y value. And in this case, the limit is L. So the limit must be an outcome of the function. It must be a legal outcome of the function. But this outcome may not be reachable for any real number other than the infinity, positive or negative infinity. That might also be the case. So if f of x becomes arbitrarily close to a single number, L, as x approaches c from either side, then the limit of f of x as x approaches c said to be L. Here we should point out an important thing. The existence or non-existence of f of x at point C has no bearing on the existence of limit of f of x where x approaches c. In fact, even if f of c is not equal to L, the limit can still exist. Let's look at the left left figure here. We have the function f of x equals to 2, so it's a constant function. where x is not equal to 1, so it's not continuous. We have a gap on x equals to 1. In this case, let's assume c is 1 and try to get the limit of f of x equals to 2, where x approaches to 1 from either side. Here f of c, which means f of 1, is undefined. It's not included in the definition of the function. But the limit is still 2, even though f of 1 is undefined. Let's look at the second case on the right side. Here we have another function, f of x, and it is 4 when x equals to 1, and it is 2 if x is not equal to 1. So we again have a straight line, but on x equals to 1 we do not have a gap. We have a point on y equals to 4. In this case, when the limit of f of x where x approaches to 1 is again equal to 2, even though f of 1 is equal to 4. These are quite exceptional points, but are not rare, so we have to pay attention. Let's give a more formal definition of the limit. It is called the epsilon delta definition of the limit. And epsilon and delta here are very small positive numbers. So if f of x becomes arbitrarily close to a single number L as x approaches c from either side, then the limit of f of x as x approaches c would be L. Here let's make the statement more clear. F of x becomes arbitrarily close to a single number L means that f of x lies in the interval lower bounded by L minus epsilon and upper bounded by L plus epsilon. So f of x must be between L minus epsilon and L plus epsilon, which also means that absolute value of f of x minus L would be smaller than epsilon. On the other hand, x approaches c from either side means that x lies in the interval lower bounded by c minus delta and upper bounded by c plus delta, which translates as the absolute value of x minus c should be between 0 and delta, and x, in this case, x could not be equal to c. So we can get things together and build the formal definition. Let f be a function on an open interval containing c, except possibly at c, but not always, and let L be a real number. Then the statement limit f of x where x approaches to c equals to L means that for each epsilon that is greater than 0, there exists a delta greater than 0, such that if 0 is smaller than absolute value of x minus c, which is smaller than delta, then absolute value of f of x minus L should be smaller than epsilon. This is the most formal form of this definition. We can evaluate the limits of a function, let's say f, using the function's graphical representation, or we can use numerical methods, or Alternatively, we can use analytical evaluation methods. In this video, as I said earlier, we will focus on graphical evaluation methods, and we will also touch some numerical evaluation methods, but we will leave analytical evaluation methods out of the scope. Let's look at how do we evaluate limits of a function using its graphical representation. On the left side, we have one example function, which is f of x equals to x squared plus 2x minus 2. And just underneath, we have the graphical representation of the function. So the question asks us to find the limit of f of x where x approaches to 2, positive 2. Here, the graphic of the function is a parabola, as you see. And on the graph, if we try to approach to the point where x equals to 2 from either side of the parabola, either side of that point, we observe that the value of the function, which is the value on the y-axis, approach to 6. So this point on the parabola would be 2 and 6. So value of the x axis would be 2 because it is given in the question, and the result, the limit should be 6. In this case, the limit is exactly the same as the output of the function. So the limit is included in the outcome set of the function. Let's look at the second example. Here, again, we have the same parabola, but there is a difference in the definition. F of x equals to x squared plus 2x minus 2, but x is not equal to 2. So we have a gap on the line of the parabola here, and this is a parabola with a hole or gap. It's not a continuous parabola, but again, if we try to approach the point where x equals to 2, we are on the y-axis, on the vertical axis, we are actually approaching to 6 again. So 6 is not included in the outcome set of the function, but we still get the limit as 6. So once again, the existence of a limit at a given point is independent of whether the function is defined at that point or not. Here we continue with another example where f of x is defined as x squared plus 4x plus 3 over x plus 1 in the denominator. This rational function is undefined at x equals to minus 1 because when x is set to minus 1, the denominator goes to 0 and it will be undefined. However, x equals to minus 1 is not a vertical asymptote. Rational functions can have point discontinuities as well as vertical asymptotes. If the rational expression can be simplified, the function is still not defined at this value of x, but this discontinuity becomes a point rather than a vertical line. So this is a good point to move in many situations. So if we factor the numerator part, we will get f of x equals to x plus 3 times x plus 1 over x plus 1. So here we can get rid of the x plus 1 on both numerator and denominator parts. Cancelling like factors, we will get f of x equals to x plus 3. So this is only a straight line, but f of x is still undefined at x equals to minus 1. So there is a hole in the graph at the point -1 and 2. Even though f of -1 is undefined, limit of f of x where x approaches to -1 is still 2, and it is easily observable from the graph given on the left side. We have the line, so it's not matter if we have a hole in the line or not. So the limit still approaches to the same point on the vertical axis. Let's try to graph a function with a given limit and do the same thing from the opposite side. As an exemplary case, let's draw the graph of a function such that limit of fx where x approaches to 3 is equal to -1. So we will sketch any function that approaches 3 and 1, the point 3 and -1, from both directions. And the simplest example is the straight line, so that f of x equals to -x plus 4. So this function will yield -1 if we substitute x with 3, and we can easily draw it like in the leftmost chart. So here we have f of 3 equals to -1, and we can easily draw the straight line representing this function. But it could also be like that. As an example, f of 3 would not be included in this function, and we could get a line with a hole on the point 3 and 3. This would be another case, but the result of the limit would not change. And likewise, if we assume that f of 3 is undefined, the result would still not change. Even if we have a hole in the line, the result of the limit would be the same. So these are the 3 cases where the same function, where the different variations of the same function would give the same limit. But some functions do not have limits, or parts of some functions, or some points within some functions may not have a limit. Limits do not exist when f of x approaches a different number from the right side of c than it approaches from the left side. This is one of the main reasons. Another reason would be f of x increases or decreases without a bound as x approaches to c. Or otherwise, f of x oscillates between 2 fixed values as x approaches c. In all these 3 cases, there is no limit for that function at that point. So we will consider these cases mostly graphically in this course. We will now explain how this first case affects the limit situation of a given function. Let me read it one more time in the previous slide. If f of x approaches a different number from the right side of c than it approaches from the left side of c, in this case there is no limit. So let's look at the function f of x equals to absolute value of x over x. So this function is clearly undefined at x equals to 0, because in this case the denominator goes to 0 and the result would be undefined. Whenever x is greater than 0, this function will be 1. because absolute value of x would be positive x and denominator would also be positive x, then the division would be 1. And this translates as approaching 0 from the right side of the function, where the function is defined as absolute value of x over x, then the limit would be 1 from the right side. And this is called the right-hand limit. But whenever x is smaller than 0, the numerator part would be positive because it is the absolute value of x, and the denominator part would be negative, so the result would be -1. So approaching from the left, the limit of fx where x approaches 0 from the left would be -1, and this is called the left-hand limit. And here we observe that the right-hand limit is not equal to the left-hand limit, so they are different. And if you look at the graph of the function on the left side of the slide, you will see that very, very easily. So the function basically consists of two different straight lines. They do not merge at a point, and the left part of the straight line represents the negative numbers, and the right part represents the positive numbers on the x-axis. And the outcome, since this is not a complicated function, the outcome is always either 1 or -1. The result of f of x is either -1 or +1. And it's not defined on x equals to 0. But if you try to approach to 0 from both sides, you will get different results on the vertical axis. So from the graph, it is very, very clear that we do not have a certain limit here. In short, when the behavior differs from right and left, the limit does not exist. Now we will see an example for the second case, and the second case is f of x increases or decreases without bound as x approaches to c. So in this case, the limit does not exist either. The given function is f of x equals to 2 over x minus 3. So as you already noticed easily, this function is undefined at x equals to 3 because the denominator goes to 0. So it can also not be simplified. There is no factor option here. So there is a vertical asymptote at x equals to 3. And let's look at the graph of the function on the left side. Here we have two asymptotic curves, and approaching 3 on the x-axis, approaching 3 from the right, f of x increases without a bound, so it goes to infinity. And in contrast, if we approach 3 from the left side here, f of x decreases without a bound, so it decreases until it reaches negative infinity. So in this case, again, we cannot match the limit on the right hand side and left hand side, so it's a similar logic here. We say that there is no limit, and alternatively we can also conclude that when the function increases or decreases without a bound, the limit does not exist. So both statements hold here. For the third case, we do not have a specific example, but the third case was about oscillations. If f of x oscillates between two fixed values as x approaches c, we do not have a limit. So you can just basically think of a sinus function or cosinus function. They have oscillations between -1 and 1, and in this case they do not have a certain limit because there is an oscillation. Limits are a fundamental part of calculus, just like derivatives and integrals. And the limit of a function at a specific input value c is the value of the function as you get increasingly closer to c. But please pay attention, the function need not be defined at this input value c. It could be defined or may be defined or may not be defined. If the function is defined at c, the limit value and function value need not be the same. Limits can be evaluated graphically, numerically, and analytically. And limits do not exist if the function approaches different values from the right and left, if the function increases or decreases without a bound, or if the function oscillates between two fixed values. So until here we focused on evaluating limits by studying the graphs of function, and now we will look for a little bit numerically approaching x from both directions. And we will do that over an example. We will try to estimate the limit of a given function using a numerical approach. For numerical approach, we usually use a table, or of course we can get help from calculators or online tools, but if we do not have such tools, it's a good option to prepare a table. So the question asks us to prepare a table and estimate the limit of the given function numerically, and the function is 3 times x minus 2, and our c value is 2. So the question asks limit of 3 times x minus 2 where x approaches to 2. Here f of x is 3x minus 2, and then we construct a table that shows the values of f of x, so y values, for two sets of x values, and one set that approaches 2 from the left side and one that approaches 2 from the right side. So basically what we do is we just give numbers for x and calculate the result for f of x. And if we prepare the table and start making calculations, we will see that the results will concentrate on one number. The results will point out a specific number for the limit. So for if we assume x is 1.9, then f of x would be 3.7. If x is 1.99, which is much closer to 2 than the previous one, the result would be 3.97. And for 1.999, the result would be 3.97. So we are getting closer and closer to 2. And for the right hand side, if we give 2.1 for x, we will get 4.3 for f of x. And if we set x as 2.01, then the result will be 4.03. And for 2.001, we will get 4.003. And as you see, for both sides of the row, we just approach to 4 as we approach to 2. So as x approaches to 2, f of x approach to 4. This is as easy as observing the graphical representation of the given function, but requires a little bit more calculation intense operations. From the table, it appears that the closer x gets to 2, the closer f of x gets to 4. So you can estimate the limit to be 4. And the figure below illustrates this conclusion with the graphical representation of the given function. Here we can just prove our estimation using the graphs again. Here we have the straight line of f of x equals to 3x minus 2, and here for x equals to 2 we get 4 in the function and also in the graph. As you have already realized, sometimes we can safely make a direct substitution with c and x. So in these cases, we can simplify the limit of f of x where x approaches to c as f of c. In such cases, the limit can be evaluated by direct substitution. That means that limit f of x where x approaches to c could be very equal to f of c. So we substitute c for x. And there are many well-behaved functions such as polynomial functions and rational functions with non-zero denominators that have this property. So for numerous functions, we can use this direct substitution. It will be very helpful for many problems, but not always applicable. So please check the properties and just do not directly assume that it is possible for every single function. The following list below includes some basic limits, which are very handy to memorize. Let b and c be real numbers and let m be a positive integer. Limit of a constant function could be defined as limit of b where x approaches to c equals to b again. So limit of a constant function would be the same as that function. Limit of the identity function would be quite different. Limit of x where x approaches to c would be c. So this is where we can replace x and c. And we also have another basic limit for limit of a power function. Limit of x to the nth power where x approaches to c would be c to the nth. And let's look at limit of a radical function. Limit of root of x of degree n where x approaches to c would be root of c of degree n for n even, and for n is even and c is larger than 0. And this list can also include trigonometric functions. For example, limit of sinus x where x approaches to pi could be sinus pi, which is 0. And limit of cosinus x where x approaches to 0 could be cosinus 0, and which is equal to 1. These properties are very handy, and if you can memorize them, they will help you a lot when dealing with limits and derivatives. By combining the basic limits we have seen in the previous slide with the following operations, we can find limits for a wide variety of functions. So again, let b and c be real numbers and let m be a positive integer, and this time let f and g be functions with the following limits. Limit of fx where x approaches to c is L, and limit of g of x where x approaches to c is K. So the scalar multiplication would be limit of b times f of x where x approaches to c is b times L. So we can just multiply the limit with a scalar. Sum or difference. limit f of x plus or minus g of x, where x approaches to c, would be L plus or minus k. So we can just add or subtract the limit values of the functions. Product could be defined as a limit of f of x times g of x, where x approaches to c, could be L times k. So we can also multiply the limits of the given functions. Quotient, limit f of x over g of x would be L over k if k is not equal to 0. And the power would be a limit of f of x to the power of n, where x approaches to c is just L to the n. These are also very handy. If you cannot memorize them, I advise you to be suspicious about these and look for your books or online sources to get these properties right. We have also included some example questions here for you to study, but I will not solve every one of them one by one, but we will have solutions of these questions. So I suggest you to stop the video here and try to solve these questions, find the limit of each given function here, and compare your answers with our given answers. Here we have the solutions and the solution steps also. In the examples, we provided algebraic solutions. But to verify the limit in example A, for instance, numerically, we could create a table that shows the values of that function, which is x squared, for two sets of x values, one set that approaches 4 from the left and one that approaches 4 from the right, as shown below. So if you prefer to solve the question using a numerical method, it's also fine, and it will work very well. And here we have the table for reference purposes. And we can also prove that using a graphical representation of the x squared function. And here we have the graphical representation of f of x equals to x squared, or y equals to x squared function. And here, if we approach to 4 from left or right part of 4, we will get the answer on the y-axis. We will give one more generalized property and we'll finalize the course here. As I said before, the limit is a huge topic. There are too many details, too many subtopics, and too many applications. But we have very limited time, and these short courses are being made to remind some topics to you, not teach these topics from scratch. So we have to cut it here, but if there is demand, we can continue diving deep into the details later. So the following statements summarize the results of using direct substitution to evaluate limits of polynomial and rational functions. So if p is a polynomial function and c is a real number, then limit p of x where x approaches to c is p of c. And if r is a rational function, r of x equals to p of x over q of x, and c is a real number such that q of c is not equal to 0, then limit r of x where x approaches to c equals to r of c, which is equal to P of C over Q of C. So these two statements are very generalized forms of solving limits of polynomial and rational functions. That's all for today. Thank you very much for listening.